here we're going to investigate the properties of some trig graphs. And we are particularly interested in two functions. And those are our sine functions and our cosine functions. So these have a really similar shape, so we're going to kind of lump these together to start. And I've already kind of hinted in previous lessons that if you sketch these, they have this kind of wave shape. They're called often periodic functions because they repeat kind of periodically. I want to investigate why this function has this shape. When I learned this growing up, I graphed this by hand to figure this out. You probably don't need to do that, but it's important that you understand why this function like this. By the way, if I continue my x-axis, this pattern repeats forever. Okay, so it's a wave function all the way as x approaches infinity. It continues to do that kind of periodic increasing and decreasing. Okay, so here's why this is the case. So to help us understand this, I've grabbed a unit circle image, but notice this is a unit circle that just has sine in it. So we'll focus on just sine x for now. And so what we see, right, imagine we are starting at the 0 of the unit circle and we are going around this way. That's actually the order in which we would plot these points if we were starting at the origin. So if I drew this graph, I would start at, obviously, x equals 0, sine is 0, and then I might go by just multiples of pi over 4, just to make my life a little bit easier. So root 2 over 2 is a little bit more than 1/2, and that would be at pi over 4. And then at pi over 2, sine of x is 1, right? So we're starting to see it, we're making a little hill here. Then at 3 pi over 4, we're again back down at root 2 over 2, which is a little more than 1/2. And then at pi, we're back down at 0. Right? And then as I continue, notice my values start to get negative. And then I could plot the other half of this too. So this would be starting at 0 and going to negative pi over 4, which is the same as 7 pi over 4, right? Negative pi over 4 is going to be, I should have written that up here probably. Negative pi over 4 is going to be negative root 2 over 2, so a little less than negative 1/2, or a little more than negative 1/2, I guess I should say. And then negative pi over 2 is going to be negative 1, that's this point, right? And so on. So we can see how we get this shape when we plot these points. Okay, so the cyclical nature really comes from just walking around the unit circle over and over, right? Because we know that walking around this full 360 degrees brings us back to 0, right? So a full trip around the unit circle is really from here on my little sketch, and then one full cycle, so all the way back to here. So notice we get a peak and a trough. So that's where the shape of this comes from. Here's a great visual that sort of illustrates the relationship between this unit circle and the graph, right? So you could almost picture this circle kind of rolling along, and the y value the function takes is the point on the circle that we are at, right? So that's where this wave shape comes from. And again, we can roll this circle as many times as you want. Because for example, 3,600 degrees is just 10 times around the circle. So it's 360 10 times. So what we want to focus on in this lesson are some of the just basic properties of these graphs. So we're going to zero in on just 3 of them today. So 3 main properties of trig graphs. The first is the midline. So the midline is the average value that the graph takes, and it's the middle between the peaks and the troughs. So on my original example, the midline would be just y equals 0, right? Because this graph oscillates around this line in the middle. But we could imagine that I could shift this graph up or down and it would have a different midline. The second property is the graph's period, which is the change in x required for the graph to make one full cycle. So our original sine function has a period, we'd say, of 2 pi, going back up here, because it goes from 0 here, x equals 0, to start, and then one full rotation on the unit circle is 2 pi, right? And that's what it takes to get from 0 to this point, x equals 2 pi. Okay, so that is this graph's period, because that's how long it takes to make one full rotation. And that's useful too, right? Because then you know this point is 4 pi, and then this point is 6 pi, and so on. Okay, and then our last property is amplitude, which is the height of the wave's peaks and troughs. Okay, so in other words, how big the wave is from the x-axis. So our original function, remember we said this highest value you can reach is at y equals 1. So its amplitude is 1. Okay, but we could imagine it gets taller or shorter if we kind of stretch this wave out. That, by the way, is why like the stereo or like guitar, something you plug a guitar into, is called an amplifier, because it makes those waves taller, the sound waves that the instrument produces. Okay, so let's add a little visual to this. Make sure you have this in your notes, and then we're going to try some problems. And really, we're just trying to explore these properties and how they relate to a function. So here's a nice little visual that captures all 3 of these ideas. So take a second and make sure you have these 3 ideas captured, and then we'll see what our problems look like for this first one. So the idea here is to sort of explore the properties of these graphs. So what we will find, right, is that one of each of these values sort of controls one of the properties we were just talking about. Just like slope and your y-intercept in a linear function, those parameters control how your graph looks, right? So you'll play around with this some. And it has this try button, right? So you can't really get these wrong. You can keep trying until your graph looks like how it should look. But you're going to change these boxes and see what happens to the graph. So as I look at this, what I notice, right, is that the center of the dotted graph is at y equals 1. And I'm thinking, well, that's kind of like, it's a shift upwards of 1, right? So just like a y-intercept of 1 shifts the line up 1 unit from the origin, I'm going to try that. And I can try before I've filled in any of the other ones. So notice my graph shifts up, and now it looks about lined up where I want it to be. So the center of my wave is lined up with the center of the big wave, right? It's still not quite the right size, so I need to figure out the correct amplitude, but it does look like the period is correct, right? So the top and the bottom of my peaks and troughs line up nicely. So I notice that my dotted curve is twice as tall as my current one. So I'll try this. Throw a 2 in there. And that didn't quite get me there. Maybe it's a 3. Right? And there is my correct graph. So that's what you're doing. You're playing a little bit of a guessing game here. And the goal is to just begin to develop a sense of how the parameters in the function are connected to the graph. So we'll do one more. And I want a sine one this time. Sine and cosine, you'll notice, look very similar. I don't know if you caught that, but cosine generally does not go through the origin, or it has a peak at the origin, whereas a sine graph goes through the origin to start a plain old sine graph. Otherwise, they share pretty much the same properties. So what I noticed with this one is that it's the same graph, but just shifted down one. So we'll say -1 here. We'll try it out. And it shifts down to my dotted line in a very satisfying way. So I got it. What you will see is that for any of these functions, sine or cosine, amplitude is related to this first parameter, which makes sense. If we multiply the whole function by something, it gets bigger or smaller, right? Midline is sort of related to that y-intercept term, or what we expect to be the y-intercept to be. And period, most of these will have the same period, so your standard 2π period. Period is related to this parameter in front of the x inside the function. So that sort of stretches the function out or compresses it. Okay. So capture this and then jump in. I think you'll have an easy time with this to start.